Okay, so the first lecture today is about going into the details of this WebAssembly meta protocol of Substrate. It's a relatively long one, so it's divided into two parts. We're going to start with part one. Before getting started, a small personal opinion here. I personally think that the way Substrate and Polkadot-based technologies are standardizing the idea of let's put the blockchain state machine on-chain, the same way that smart contracts were placed on-chain, is a big deal. And I think it's only a matter of time before more and more ecosystems, more and more blockchains or similar systems start doing the same. So it's a bit of a personal opinion. Today we're going to learn a lot more about this runtime and node division and how they talk to each other. I think it's worth repeating some consequences of this as well, what it really means. It's the most important design choice of Substrate, as in it impacts everything. And there is something inherently negative to it, as in it's like one fixed opinion that you have to buy into. There are some downsides to it as well. It's one strong fixed opinion, but it unlocks everything else to be flexible. So by accepting that, okay, I'm going to split my system into this meta protocol and high-level protocol, this design choice is fixed, but then a ton of other things can become flexible. So there's a trade-off to it as well, and we're going to learn more about it today. Okay, so this is the diagram that we had yesterday. I'm going to pause again, maybe for 30 seconds or something, also to see if any questions pop up. But today we're going to heavily focus on the part that has been highlighted red, like the communication between the node and the runtime. We also learned the names from them yesterday, runtime API and host functions. Okay, so apparently not. That's good. Short recap. What were host functions? Host functions are the means that runtime has to talk to its node, to talk to its host, to talk to its whoever is running it. Runtime APIs are the opposite. They are the set of functions that the runtime exposes for the node to be able to call into. You've seen a couple of these already in your assignment, or in your assignment you may have seen at the bottom of your main file there's a big macro that's called IMPL runtime APIs. Something like that should ring a bell. Another important point that we should recap before going further is the notion of database and state. The fact that database is kept on the node side, so all the blockchain data is kept on the node side in this component that we typically refer to as the database. But inside the database, we have individual states from different blocks, and these states are opaque key value pairs that the node itself cannot really interpret, and the runtime understands them. A very short recap of everything that scale is as well. If you want to really boil it down to one diagram, it's this: that scale is all about encoding and decoding to known types. You have a known type like U32, you encode, you get some bytes back, then you can decode those bytes back to a known type again. Okay, so the way that the next section of this lecture is going to work is that I'm going to explain three main scenarios that the runtime and the node want to communicate together in it. And they are taught using some pseudocode. So I will show you first a block of code. I'll give you a minute to read it. It's documented. All of this is pseudocode, as in you should read it as plain English. There's no expectation for you to, pseudocode, so not real code. And then we're going to walk over it and go through details. So the first example that we want to talk about is updating the state. One of the things that you learned yesterday is that through the process of executing blocks, the runtime will want to update the state. For example, if this transfer that we saw yesterday from Kian to Bob or whatever happens, at some point through that execution, the runtime wants to tell the node, hey, update some state for me. So give it a look. I'm going to wait 1 minute. So hopefully this one is fairly understandable. Let's start and go through it step by step. So the first detail here is that it's the runtime that knows at which location in my state, at which key, for example, Kian's balance is stored. In this case, quite arbitrarily, I chose Kian_balance. It could be anything. This is the key in my state that is storing my balance. And the runtime is the one knowing this. I mean, what it is, it's up to the runtime to decide on that. Again, in your assignment, you've been given this specification of like account balances must be stored under this particular location. And this key is encoded as a VEC-U8, as bytes. The next step is that the runtime then actually need to give this key to the node and say, well, give me the value that corresponds to this. And this is where we are kind of through this example learning, there must be a host function through which you can get some state, to which you pass in a key and you get some raw bytes back. It's also important that the return type here is raw bytes because the node who's giving you this value or this host function itself doesn't really know what it is giving to you. It's just like looking into the database, giving you these bytes that were correspondent to this key. Then the runtime actually knows, okay, these bytes I just received are a U128 value. Again, similarly in your assignment, you've been told what numeric type you should use for balances. Similar to this, it's U128. And then the runtime decodes those bytes into U128. Then the next step is self-explanatory. We update it. And then we basically do the opposite. So the runtime now has this new balance, wants to then write it back to the state or tell the node, hey, I have done my thing. You should now update it in the database for me. So the updated balance, we encode it. And then finally, there's another host function that, in the last line, that sets a value this time, to which, again, we pass the same key and some bytes that is the corresponding value. So needless to say, you would, let me first get to the next slide. Again, we conclude here that there must be a set of host functions to get and set from state. So this is the first set of host functions that you should know they exist, and you should also use it in your assignment. Later in this lecture, you will actually exactly find the functions, so you would know the names as well. But something similar to these two functions exists in Substrate. Has anyone already, like, for example, seen the corresponding host functions in the assignment? Because it is in your test. If you look close enough, you'll... All right, well, you will see it today. A small detail that exists is that why are all these host functions, again, like so opaque? They all operate on the basis of key value. Why is there no host function called setBalance? Does anyone want to try and answer this? Where is the...
It should be a bit... Oh, no, it's working. Is it specifically because we use accounts-based model, so it makes sense to have an account and has a key and the set function, like the set functionality for that thing.
Let's continue. I didn't get what I was...
I think it's because the node doesn't know what our account ID is or what balance are we managing, or...
Yes, so that's what I wanted to get at. So, I mean, if there was like a host function where you could directly tell the node, set the balance of this guy to this, well, initially the node, by true specification, shouldn't know this information. The node shouldn't know that balances are U128 or account IDs are 32 bytes, whatever. But even if we kind of like hard code it, then we are destined to remain with it, because then it cannot upgrade over time. So we had the... Yeah, I also mentioned this yesterday. This is just a recap that some exceptions exist to this rule. For example, you can even there's a link to literally where in Substrate's code this exceptions are listed. It's like a mod called well-known keys, and one of them is code, and it's literally like colon code. So colon code in any Substrate-based chain is where the runtime is stored, and this is a key that the node software also is aware of. It knows about it. But yeah, everything else like balances, accounts, the node is like, I don't know. So again, a recap. This diagram, I think, conveys this message really well. Make sure you understand it. Okay, first example, easy, right? So let's take it to the next level. Now we're going to look at block import. So the process of importing a block that you have not authored yourself. So you're a node sitting in a network just doing nothing particular, but everyone else, the main validators who are authoring blocks are sending you their blocks and you just want to import it. You want to update your own state. Before going into the example itself, I want to pose a sort of, give you a new fact. We already established that the node's view of the state is opaque, as in the node doesn't really know what is this state, it's just some key values. What do you think is the node's view on transactions? So if, for example, there's a block and there's a transfer in it, can the node itself interpret and know that this is a transfer? But why? Or what is the elaborate. Yeah, the answer is no, but let's pass the mic.
Thank you. Because there would be a database update, which the runtime would be the one handling, not the node.
So let's imagine all transactions are no-op. They don't do anything. I'm just saying a block comes in and there's a transfer in it. Should the node actually see that it's a transfer? Let me forward to this. So we already established that the answer is this. The runtime looks at a block and knows what it is. But the node looks at the block and the transactions are just some bytes to the node. What does that imply? I can say it myself. Maybe it's a bit too early for it. So similar to the state, there's a trade-off here. Anything that the node is unaware of, like the state, like the transactions, they can upgrade without the node also needing to care about them. So typically what we want in substrate-based chains, we want our state transition function to be upgradable. So the runtime needs to be upgradable. And part of the state transition function is the body of the blocks, is the list of transactions. So if we want to be able to upgrade our transaction format, if we have a transfer and we want to, like, for example, switch the parameters or add a new parameter to it, if we want those upgrades to be able to happen forklessly, the node cannot know about them. The node should only see them as some bytes. So I will recap this fact again further in this lecture, but that's the short answer. Whatever we want to be able to upgrade forklessly in this beautiful WebAssembly code upgrade manner, it needs to be opaque from the perspective of the node. Let me see if I missed anything here. No. Okay, so we can establish that this is also, again, pseudocode, but have a look. It's kind of self-explanatory. What I'm trying to convey is that the data structure representing the block on the node side, it has some transactions, but it's a vector of bytes that I just really don't know what to do with. Whereas when on the runtime side we are about to execute the block, it could also be the same data. We would actually be able to then decode those bytes into a known transaction type and execute them. Where's the second one?
So it's like node always sees bytes only, right? I mean,
for transactions, yes.
For transactions and And things we discussed earlier also, right? Before that, before transaction, right?
So the state is also opaque.
State, yeah.
So far, we've learned that state is opaque to the node. Transactions are also opaque to the node. Right? Oh, yes.
Yeah. Hello? Yes.
Yeah.
So when we say block import, that means that when the node gets some transactions and want to start doing the state transfer with the runtime, or what do we mean exactly by block?
By block import. So block import is when someone else already authored a block, they give it to you, and you just want to import it and verify that it is correct. I haven't got to the example yet. So I think when I describe the example, you'll get the answer.
Thanks.
All right. So let's actually get to the example. So this is a sort of the pseudocode. Again, have a look at it for 30 seconds or so, and then I'll walk over it. So again, this is, I mean, I've chosen some of the names intentionally, but it's not like you need to know, oh my God, what is import queue? Like, it doesn't matter. Like, it's a queue of blocks that are waiting to be imported. Like, what it is, we don't really care. But point being, there we ask this component, give me the next block that wishes to be imported and has not been imported yet. So if one exists. And this next step is, let me do it one step at a time. This next step is kind of new. So next we want to actually execute this block. So we need a runtime. We go to our database and say, okay, from those well-known keys, the keys that we actually know about, give me the code, please. And then we stick that code into something that is like a WebAssembly executor or, builds the runtime out of that code. Again, these are details that we can abstract away. I don't know myself how this WebAssembly executor stuff works under the hood. That's fine. We don't need to know it, but it creates the WebAssembly virtual machine given the code that we have just given to it. And finally, we can establish the first runtime API that every runtime needs to have, which is, okay, you're a runtime, right? You should be able to execute blocks. Here it is. Execute a block for me. Is this all clear?
So in line number 5, are we accessing the key code from the database first? In line number 5.
Yes.
Okay.
Although there's a small mistake in that line, which is my next section of the slide. Can anyone already guess what is like sort of missing here? What is
Node?
node?
Yeah.
Let's continue. You'll see it. I mean, there could be, I think these could also be valid answers, but there's one particular missing detail that I'm looking for. So first we establish, okay, there needs to be a execute block runtime API somewhere in all of our runtimes. The detail that was missing and I was looking for, I'm hinting at it here with this diagram. Maybe this will help now someone answer the question. So when we say, give me the code, there's a question of which code? Right? Because code is part of state, and there's the state of last block, the block from week ago, Genesis, like, the code is part of the state, and there's one state associated with every block. So generally speaking, every time you talk about state, or then consequently runtime, you need to say runtime at which block. I mean, usually when you don't specify it, you mean the latest, but here we should have specified it. So if we were to specify that notion of latest block, our pseudocode would turn into this. Have a look, please. You need to hold the...
Okay, hello. So you have two ways of get things from the database. You can directly get a key, like with the get method, and in this way it will get the last value of the last state.
Although that was hypothetical and non-existent. Okay, all of this is non-existent again. This is all like...
Just on this example, I see that you state get, and then you get something that supposedly is the last. It belongs to the state that you passed in the database state at.
Yeah, and this is not accidentally the last. It's because we gave it the parent hash, right? So that's a hash of the last block that we want to build on top of. Continue?
Yeah, I mean, in the previous code, you didn't have this.
Yeah, and the previous code was, in my opinion, actually a little bit, I would just call it wrong. As in, it's nonsensical a little bit, right? But yeah, we can establish, for example, in these pseudocodes, if you don't specify, it's the latest. But I would take it a step further and just say, this is wrong. Scratch this. Forget about it.
Okay.
I think it's better for your understanding if you just take this as...
So you always need to pass the block that you want the state of, right?
Yes. Or I would rephrase that as... I think I literally have this sentence somewhere in these slides. When you say... state at, like when you want to talk about the state, you always need to specify state at block n.
Okay.
Right. Okay, so let's walk over this. First line, similar, give me the next block that wishes to be imported. Now this example now hopefully illuminates better why blocks need to specify their parent hash. Because blocks are a valid state transition on a particular parent block. I mean, if there's a temporary fork, it could be that a block is not importable on, or a block is valid in one fork but is not valid in the other fork. So every block has to specify, I am this block, here's my transactions, and if you import me on top of this particular parent hash, you will arrive at this state root and I am valid. So that block is itself specifying its parent hash, and when we want to import it, we actually go and fetch the state associated with the parent hash, and this state is our starting point. And now we're going to build the new block on top of this state. So,
questions. So like in the state example, there's like host functions get, and then here in here we see like database state at, and then state is inferred from that. I'm just like not clear exactly on like what are the functions that the node exposes to the runtime that can be called, because here we have host functions get, so that's just like getting a key, getting a value for a key, who knows from where, and then there's database state at. So what are those APIs? And
yeah, so these are, this code is all on the node side, or these operations are all happening on the node side. Only on the first example we had this, like the code was as if it was in the runtime. Now we're looking at this purely from the perspective of the node side, and we only call into this like runtime dot some runtime API. And inside of this runtime API, we go into the first example's point of view, where, for example, this execute block internally is probably calling into like, host function, set, someone's balance, whatever.
So this database state at, and like these are basically like some static functions that are available to the node, right?
Yes.
And in the previous one again, like with the host functions, so that's actually something that would be happening on the
inside the runtime, which we don't see here. Again, this code is, this pseudocode is as if it's all happening on the node side, or it's on the from the perspective of the node side.
So what is this host functions concept like?
So inside execute block, which we don't see, we probably are going to update my balance.
Yeah.
That will happen through a host function.
Okay.
But we don't see it here because this code is now at the perspective of node.
So like database and state, Wasm, that's like node side concepts, and runtime side is host functions or something like that.
It's a way to put it. Let's put it.
It's okay. It's just sure. Okay, cool. or available from, because the host functions is like an API. Okay, later.
Yeah, we can talk about this after class. Yeah. Okay. So I think we were at this point, or let's recap quickly again. So we get the parent hash, we get the state associated with the parent hash. So this is the last state on top of which I want to build. We get the code now from this state. So this is the last code, and we build a runtime from this last code. And then I'm representing this as like a closure. This is also not accidental. Like you will see a similar code in Substrate as well. But what I'm trying to represent here is that on top of that state, we execute some runtime API. So whatever updates happen via these host functions that he was talking about inside of this execute block will trigger changes in this state variable. It's like I'm trying to now represent this in my pseudocode using this closure format. And finally, this state variable will get updated while we're doing execute block, and then we store it back, this time no longer as the parent hash, this time we store it back into the database with the block header hash, so current hash. Right? So this will become now the new state associated with the hash of this incoming block. No longer the parent, but the block hash itself. Maybe it's good to show you everything again and wait for more questions. Yeah, can we pass the mic back there? Throw. I don't feel like the second one is being used there. Maybe we should bring it. Okay, but I mean, that side is not asking questions, so they lose their...
Okay. One question. I don't get very clear. So the code, it's actually a WebAssembly code that comes in one block from another node.
No, the code is not in the block. The code is in the state.
The code is in the state.
Yes.
But is specified then which... So in the block, you and me are nodes. So you send me a block.
I send you a block, yeah. You already have your state, and in that state, you know... So my block says, I'm a valid block on top of block 100. So you have the state associated with block 100, but you have not imported my block 101. You go to your state 100, which is my parent state, get the code from there, build your runtime from that code, and then with that code, you should be able to import my block, if it's valid.
Okay, I think I get it. Maybe. Okay, but what happens if you have more than one runtime in a node?
Yeah, I think we had this question yesterday. So you have, every state has its corresponding runtime. Thank you for closing the door. If that's not what he went to do. Okay, well, maybe someone can close the door. What was I saying? That so my block is 101. There is only one canonical state 100. Everyone knows it, everyone has it, and in canonical state 100, there's one runtime. So I got this question yesterday as well, and I'm trying to really push back on it because I think it's a misleading way of thinking of it. Oh, what if there's 3 runtime? Well, that's like saying, what if there's 3 different opinions on how much Bitcoin I have? Well, it's not a blockchain. Well, it is a blockchain. It's a fork in a blockchain. Like it's different opinions. It's then.
Okay. Okay.
Hi. Question. So somewhere between like storing this new state, the state root is like compared to the output of execute block?
That's a very good question. I think I even want to hint at it. So what is the main thing that happens inside execute block is what he's referring to. So what does execute block do? Execute block will re-execute all the transactions in this block. This is like a recap of what you should have learned in module 3, or rest of this course, let's say. Execute block internally will re-execute the transactions, then calculate its state root. from its local state, from what it knows, and it will check with the block header, is this the same state root? And then if it's a match, it's a valid. If not, it will. And you will see, you have exactly this code. If you look at your assignment, the execute block is already implemented. The comments also say, this is already done, you shouldn't change it, and it does exactly that. Maybe the only thing that is a little bit new, I'm guessing you guys know less about extrinsic root or transaction root. Transaction root. So it's the same concept, but for transactions in the block. So every block in its header must place a Merkleized root of all the transactions. This comes from Bitcoin also, like this has been always the thing. This is also something else that is checked in execute block, and you will again be able to, you will see it in your starter code. Now in the assignment, your main task, for the first step at least, is to make sure your author process and your import process match. As in, if your runtime authors a block, it puts the correct roots in the header, such that if the same author, if the same runtime, 10 minutes later, re-imports the same block, it comes up with it's a valid operation. It's actually the main thing, the only thing you have to do in your first step. Equal. Yes.
Thank you.
Actually, I have a question that, depending on your answer, can be followed by another.
A bit louder.
I have a question that is, these nodes, they are like validating the blocks that they receive from other nodes, but are they the same nodes that can author blocks?
It's up to I would say that's, the answer is, I would say, irrelevant to the things we learned here. The same, you could have a distinction where only specific, like it depends on your consensus algorithm and properties. You could have a network like Bitcoin where everyone with both importing stuff and authoring, right? In principle, every miner, even if you have like a fraction of a hash power, every 10,000 years you will author one Bitcoin block.
Yeah, but I mean in the aspect where if this node doesn't know, like he doesn't understand the transaction and the states changed, how can produce a block if you don't know that Alice is sending something to Bob?
So how we author blocks if the node doesn't know transactions and so on. So that's the third example and the last one. We're going to look at block authoring. So maybe wait until that. But a short answer, you can guess it yourself. Will the node be able to author blocks on its own without using it at runtime? Exactly, because the node doesn't even know like what these transactions are just bytes to me. What am I going to do with them? So what is the runtime API that you speculate must exist to enable that process?
Is a way to translate that in a way that he can understand and.
Yeah, that's one way to put it. Or there is a runtime API to execute transactions one by one. So imagine you're the block author. You want to author a block. You get the best runtime upon which you want to build a block, and you give it transactions one by one. You just give one and be like, is everything good? And then if the runtime says okay, you say, okay, here's another one, here's another one. And then you'll be able to build a block.
Yeah.
And we'll see that in the next example. Okay, this is a recap of what we already covered in class, but I think it's worth repeating. State is only meaningful at a given block. You can't say the blockchain state. You can't say this key in state. It's always a question of which state, because you have the latest state, you have the previous state, you have the genesis state, and everything in between. And interestingly then, therefore, code and then the runtime is also part of the state. So the runtime is also only meaningful when you say which runtime. Am I talking about now the latest runtime or the previous runtime? But even if the runtime doesn't change, like, let's say there was a runtime at Genesis, some code, and then throughout the life cycle of a particular blockchain, this never changed. That's possible, but it could change. So therefore, we need to specify which one. And then interestingly, because runtimes are always linked to which runtime APIs are also then, you have to specify, I'm calling into this runtime API at this particular block, at the runtime of this particular block. So this we also covered. I wanted to ask at this point, what's the most important thing that execute block does internally? And the answer is checking state root and extrinsic root. And here's a visual recap of everything that learned. So let's see how it goes. So we start at step 0, as in blocks will generally be gossiped to us or given to us via the network. And how it exactly works, we don't know, we do not want to know. But the point is, we have a component in our node side, the bottom right corner. In Substrate, it's called import queue, but again, the name is not something that you need to memorize or know by heart. It's a queue of blocks that are awaiting to be imported. That's step 1. Whenever we are ready to import a block, we come to step 2, which is we look at the state of the last block that has already been imported. So in this example, it's block n. We want to import block n plus 1, but we don't have it yet. Block n is the best block that we already have. So we get the code from this last block that we had. Although accurately, it should be the parent of whatever wants to be imported. So if we want to import n plus 1, we know the parent is n, so we get the code from this particular state. From the code that we just got from the state, we initiate our Wasm runtime, so step 3. We give it to some WebAssembly executor, whatever that executor could be. There's tons of WebAssembly executors out there. Some of them are interpreted, some of them are compiled. Doesn't matter. And then finally, we pass the block, that's step 4, into the runtime via a runtime API, telling the runtime, hey, please import this, as the consequence of which the runtime may or may not call into some host functions and update some state. Yeah?
You just said that the most important thing that the runtime does internally is to check the extrinsic and state root. Could you quickly reiterate check? What does check mean exactly?
So every incoming block in its header has a state root and an extrinsic root. What is exactly, how do we interpret this? I would say that we should interpret the state root and extrinsic root that is in the header of every block as a claim, right? So the block is saying, if you execute my transactions on top of my parent hash, you will come up with this state root. And this is the root of the extrinsics that are already in there, or the transactions that are already. Let's talk about only state root for now. So it's more like a claim, and then the runtime has to re-verify it. The runtime, when we call execute block, the runtime will re-execute all the transactions, its local state will be updated, so basically this guy. The runtime will build its own copy of, okay, this is what I think state at block n plus 1 should be. It will calculate the root of this individually, and it will check if it matches what the block claimed it would have been. Does that make sense? You need to hold the...
So we're talking about the process when importing a block, not when authoring one, correct?
Now we're talking about importing, yes.
So
authoring is next.
Authoring is next, okay.
So the fifth step is to write back into the state?
Yeah, if any. I mean, in principle, maybe a block is just nothing. Like, I don't know, maybe the runtime doesn't want to, again, it's in principle, it could be nothing, but in practice, usually it's updates to the state. All right, good amount of questions. So that's...
Just to clarify, you mentioned that essentially whenever we go ahead and get the code, we have to specify the block. So does that mean that there could be some kind of logic that fetches back like a code or Wasm code from a block that's like way back, or is it always forward?
Yeah, it's on a long reorg, right? You've learned about reorgs.
Right, yeah, okay.
Right, so when we are on a fork and we suddenly like, oh, this fork is wrong, we should go back to a week ago and...
Interesting. And so does that mean then that the database is structured in a way that you essentially have also key values to the particular blocks?
I would call that implementation detail, but probably yes. Like as in there is a state associated with each block.
Okay.
With each, yeah.
Alrighty, thank you.
And in principle, sorry, I want to add this again. In principle, let's say the database is storing the states associated with the first 1 million blocks. And maybe in that 1 million blocks, nothing happened and all those 1,000 copies of the state are identical. But in principle, they could all be different. So that's also a nuance to it. Yeah.
My name is Gunjan. When Wasm runtime is writing the state updates via host functions, So it's actually making the new state. Unlike the pseudocode, you shown that the final state is written at once.
Yeah, maybe that. But no, you could also link it to the pseudocode. So let me. Yeah, I mean, this I would say this is a nitpick, but I will try and let's talk about it. But because this is a pseudocode, I wouldn't, I wouldn't try too hard to try and make sense out of it. There might be little inconsistencies like this. So I think here what I meant to say is that from our database we get this state, and this is the state at one particular block. So and then this is mute. So we're within the rest of this pseudocode we are updating this state, but we haven't persisted it yet. It's in memory, or it's not. It hasn't been written back to my database. And particularly in these 3 lines, because we have this closure situation, so whatever updates happen in an execute block are reflected in this state variable. And finally, we want to write it back, as in now it should be stick it in some disk database forever, or
Okay, so that means we iterate over all the keys in the state and then we update the keys in via host function.
I mean, maybe that's up to what host functions are triggered inside execute block. I don't see why we must iterate over all keys, but
so state is combination of key value pairs.
Yes,
and those key value pairs are residing in the database.
Sure, but if they don't change, we don't need to iterate over anything,
so only those who have changed, we need to update in the...
Yeah, and we know which ones changed because there is a host function from the runtime saying update this key, so we know we have to update only that.
And second thing in this slide also, the thing is when we import the code, we are not decoding it.
The code has a known type, it's just bytes, it's VEC-U8.
We don't need to decode it.
No. The code is VEC-U8. It's a byte array.
Okay.
Right.
Okay. Thank you.
Yeah. Okay. One more, then we continue.
So I was wondering for this case. So you said that view was node side, right? So we're trying to get the code, and then we're executing an execute block based on that current or the most up-to-date state. So in the Wasm executor, you said there's many different executors. So if this is Wasm time, or I'm not sure if that's what it's called. So if the node was updated to use Polka VM, would that be a requirement for every node to update to that? Would that be a hard fork?
Yeah. Okay. Depending on, you could, maybe it can be engineered in the backwards compatible way in some way, but generally speaking, I translate your question to what if something in the node is changing, and the answer is if it's breaking, then it's a forkful upgrade. Every node has to upgrade at the same time, or there needs to be coordination or something like that.
Thank you.
All right, so let's go to the third example, which is block authoring, which was the subject of many questions as well. So I hope you're excited to know it. But before going further, I need to drop one last jargon bomb. It would be one of the last ones, but you may have noticed we're using the word extrinsic and transaction kind of interchangeably. They're actually not equivalent. Let's have a look at what we mean by them. Transaction historically comes from database systems, but in blockchain systems, it's used because it's a statement from some external users saying that something should happen. But I think I don't know the exact terminology, but it has that inherent property that it's a statement from someone that something should happen. That's what we mean by transaction. And substrate-based chains support different types of operations that are not necessarily the statement from someone. For example, we'll see them in the next slide, but TLDR is that substrate supports a more broad category of things that can change the state, and we call them extrinsics. I think extrinsic, just if you search on a dictionary, means data coming from the outer world. It's not necessarily signed, it's not necessarily from someone, it's just external data. The diagram kind of looks like this. You have extrinsics, which is the most broad term that you can use for these kind of things, and it's categorized into two categories: transactions and inherents. I won't go into too much detail. Just want to give you a brief overview of what, for example, inherents are. You will learn a little bit more about them next week in Frame, but generally speaking, these are advanced topics that are not officially part of the curriculum, but you can search them in our documentation and so on. So I'll start with inherent. So inherent is one of the more novel things in Substrate that you don't typically see in other systems. They are pieces of data that are put into the block by whoever authored the block. And other validators, through importing that block and accepting it, they just accept that it is true. So one example of this is like a timestamp. For example, validators, when they author a block, they put their local timestamp of when I think the time is right now into the block as an inherent. We call that inherent. Other validators will check if this is like, somewhat reasonable. If it's somewhat reasonable, we accept it, and that's the timestamp of the blockchain. Or if that's a timestamp associated with every block. TLDR, it's data put into the block by the block authors. But importantly, it's not signed. It doesn't come from a transaction pool, so it's not like a typical transaction. Then contrary to inherence, we have transactions. These are information that is coming from a particular, or it's a statement coming from a particular person. It could be either signed or unsigned. And usually when we just say transaction, we mean signed transaction. Unsigned transactions as well have some niche use cases, but are very tricky because no one is putting a signature on it. Usually no one can pay for its fee. It has some very, very niche use cases that I don't want to go into the details, at least now. We can talk about it after class, though. These are both unsigned transactions and inherents have interesting use cases, or there are novel things we can do with them. So this is just a written form of what I just said. Also in the speaker notes of this slide, I explain further what I mean by each of these keywords. So yeah, transactions are a type of extrinsics, but not all extrinsics are transactions. But typically, for example, in your assignment, because we only support signed extrinsics, you can use transaction and extrinsic interchangeably, because it's the only type of extrinsics that you have. I also point at this, so why do we call it, or there's this component that we usually call to as transaction pool, or transaction queue. Why is it called transaction pool and not extrinsic pool? Because if we look at the diagram, all extrinsics are either transaction or inherents. And I just said that inherents don't go through the route of some user submitting it to someone. It's information that's put into the block by the author. So the transaction pool is really only about this category of things.
Excuse me. Could you give you one example of unsigned transaction?
Unsigned transaction. So one occasion where we use it, it's actually used to mimic inherence, or we use it to, well, let me think. No, that's not a good example. Yeah.
Can I suggest one? So host may be submitting transactions signed by someone else, so some piece of data signed by someone else, but I'm just submitting, and runtime should check it.
Yeah. Okay, that's a good example. So this heartbeats, I remember it, but I don't know enough to explain it. So I don't know. It's just like one trail for people to follow. Let me first say what he's saying. So sometimes you want transactions that are themselves unsigned, like the transaction in the outer form factor is unsigned, but within the data of the transaction, there is already a signature. And then you can actually verify that someone was behind this. And it's actually particularly useful because it allows you to, if you really know what you're doing, bypass things like transaction fee payment and so on. But then within the transaction execution, you can check the signature, and if some conditions are met, you can allow it to go through. So this allows you to program things like free transactions with a fixed quota, for example. You want to have, yeah?
Like an inscription.
Inscription.
Yeah, from like the BTC inscriptions, where you can put some kind of metadata inside the block that is not necessarily a transaction.
I'm not familiar with this inscription.
Yeah,
so
I will research, but I think it's one of the cases.
Well, share in the chats if you have something.
Yes, so I have a question on his example. So if the host already receives the transaction which is signed transaction and he submits it like an unsigned transaction, So isn't like host is also like when he's submitting the transaction, he needs to sign. I mean, to hold the responsibility and to verify in future that this host has submitted the signed transaction, transactions.
Sorry, can you rephrase?
So since we're taking the example of unsigned transactions, right? So a bunch of unsigned transactions, signed transactions which are coming to the host, and host is now submitting those signed transactions, considering that these are already verified transactions.
Oh, so you're saying some unsigned transactions come, and the host is
No, signed transactions comes.
Signed, okay.
Yeah.
Okay.
But the host is not signing it, right? So it's submitting it. This like batch of transactions which are coming as a verified transactions. Since like host is considering as a verified transaction through some, like you said, so it verifies some conditions, rules, where it says, okay, these are the verified transactions. So now it's not signing it, and
Node doesn't sign anything
no,
for other
not
people.
host, I mean
but still, like a host doesn't sign things for other people. So I'm not getting what you're.
So I just wanted to understand, like, the example of this unsigned transaction, like, the one which he gives, I couldn't understand that one, where he says like a bunch of signed transactions which are already coming in, and the host is speaking of the transactions, and while submitting, he is not signing since it already knows that it is already a verified transactions.
So let me rephrase that. I think, I can rephrase that example. So the transaction is itself unsigned, but for example, one of the part of the payload is signed by whoever sent it and contains a signature that is enough for the runtime to say, okay, I'm going to accept this. And the benefit of this is that then this will bypass things like the default fee payment and so on. But this will make sense, I think, when you, for example, see next week how transaction fee payment works in Frame, how we can specify a transaction as being unsigned and what consequences it has. Yeah, I mean, I'm realizing now that this topic, like, I want to like not go into details, but I'm also realizing maybe I should have prepared more and gone into more details, because it's more confusing to just mention them without sufficient example. But I think I have good amount of like examples and further explanation in the notes of the slide. So have a look at that. But yes. All right. So with that, let's go into the third and last example, block authoring and how that works. For this one, we're going to first look at it visually and then look at the pseudocode, because I think it's a bit easier this way. So first we have an almost identical diagram. There's some components are gone because we don't care about them in this case. And where do we start? So we start with similarly from the networking layer. And this time, what is being gossiped to us, what is being given to us by other peers in the network or users directly is just some transactions. Some like, hey, someone wants to submit this transaction. Someone wants to make this transfer. Someone wishes to, upgrade the code, even though it's going to fail. Whatever. And going to step one, what's going to eventually happen is that the transaction pool is going to be, you haven't been formally introduced to what is transaction pool. That's actually the next lecture, but you're probably somewhat familiar with it. The transaction pool is going to keep or maintain a list of transactions that are, to the best of its knowledge, good. If that makes sense. Like the transaction pool cannot know for sure, for reasons that we'll cover next, if everything is good, but it will maintain a list of transactions that are, as far as I know, like, they are not garbage, they are not purely bad, and so on. So this list gets, gets filled over time, and it's always maintained, and the pool always has this list ready. Now, what will happen next is that at some point, we go to a different diagram. Oh yeah, okay, and I actually want to cover something else here. So how does the transaction pool start filling its list, these transactions? It would actually communicate again with the runtime. So the transaction pool would, similar to all the previous steps, get the latest state that we have, and we think it's the last block, get the code associated with that state, create a Wasm runtime whenever it needs it, and as it receives transactions from the networking layer, it would ask the runtime, hey, I received this transaction, do you think it's good or not? Like, should I keep this transaction or is it garbage? So this is why we have, again, that step 3, 4, and 5. Although the 5 is not really relevant here because, we're not actually executing the transaction at this point. We're just doing like some initial checks. So again, because the node components, none of them can even interpret the transactions. The moment the transaction pool receives a transaction, it will ask the runtime, hey, is this good or not? And I will get to this further in these lectures as well, but hopefully you can already have a guess about what kind of checks we are doing at this step. And the answer is that those checks needs to be like very lightweight and cheap. Because this is the realm of transactions that are not executed, even if they have a fee associated with them, no one's paying for any of these operations. It's like freebie at this point. So the communication at this point between transaction pool and the runtime is very fast and minimal. Again, the transaction pool is like, here's a transaction, just tell me if it's like, if I should throw it away immediately or not. Like, it's not like we want to execute it and make sure it's like successful and whatnot. All right, this was like an intro into like the transaction pool stuff, but there's a whole lecture on it later today. So, yes.
The import queue.
Yes.
So in the import yeah. So what is the import queue exactly? Because
it doesn't really play a role here. If anything,
I know it's in the previous one. It's in the import block.
Yeah. So that was the example number 2 for importing a block. Now we're authoring a block in which import queue is irrelevant.
So we don't. This import queue has nothing to do with the transaction pool?
No. Or at least in this figure, it plays no role. I think I literally let them be there because, I don't know, when I was making the image, it was there and I didn't remove it. So, or it fills the gap there nicely. But
what does the import queue mean in general?
In general, it's a location, or it's like a software component in which we are keeping all the blocks that are awaiting to be imported. It's a queue for blocks to be imported. But again, in this example number 3, it's completely irrelevant. Is there more? Okay, so now imagine our transaction pool is filled with this beautiful list of transactions. Now we want to author a block, actually. So this time I shuffled some things around. I'm sorry, import queue still plays no role there. It's only, I don't know, it's, I will remove it, but it doesn't have a role. The block builder component, which used to sit down there, is now much bigger because important things are happening inside of it. And we start there. So we start with the block builder component, which is intending to build block number n+1. And it starts, as usual, as always, going back to the database and getting the latest state, and from that, the latest runtime. So the block builder knows, okay, I want to build block n+1. And I have this transaction sitting there waiting for me. I need the state at block n and get the code from it. That's step 1. And then for the 5th time in this lecture, we build a Wasm runtime from that code. So that's step number 2. Our Wasm runtime is now ready. And then what will happen repeatedly is that the block builder will kind of like get a transaction from the pool, pass it to the runtime. It's like this. So the block builder, or whatever components is, like the names again doesn't really matter, but hopefully block builder is intuitive enough. The block builder will ask the pool, okay, what is your best transaction? What is the first one that you think I should put in my block? The pool will say, okay, it's this transfer, it's very high value, it gives a lot of tip, whatever that the reason could be. That's the first one. And then the next step hopefully is something that you've also seen many times, or you can already predict it. The block builder will get this transfer, pass it to the runtime, ask the runtime to execute it, and some state changes will actually be propagated back as the results. That's step 4 and 5. And as a consequence of it, this new state is being updated all the time. And then we repeat this step as many times as necessary. Or that's implementation detail. That's very much up to how big your blocks you want to be, how much resources you have, or whatever. Yes.
When there is an upgrade code transaction,
yep.
The existing block will execute based on previous code, right?
Correct.
And so this upgraded code will be used only after this block, the next block, future
yes.
blocks, right?
Yep. So a subtle detail that is mentioned here, we'll get to it in the next lecture, is that so we have two similar runtime APIs. This is also part of your assignment. The transaction pool passed transactions individually to the runtime and asked, are they good or not? You have this also in your assignment. Maybe if you have read the assignment description completely, you'll see that part of your description, part of your mandate is actually to implement a transaction pool validation API. But then when we were doing that, we're not gonna like, all the state changes are irrelevant, like, because that's not like, when we're just validating a transaction, we're not gonna update any state. Like whatever happens in that runtime API call stays in that and it's dropped. So in this previous step, when the transaction pool was being filled, we also asked the runtime to validate these transactions for us, but whatever the runtime does for them, that step 5 that I have there is actually like not very real, as in we don't update any state. Whereas when we are actually moving the transactions from the pool to the new block here, some state is actually being filled and it's being updated. It's what I have here. So there are two similar runtime APIs, but they serve very different functions. One of them is used for block building. It's called apply extrinsic. You will see it you have seen it in your assignment. The other one is called validate transaction, and they both operate on one transaction at a time, but doing two very different things. Okay, and what's the next step here? Like, let's say the pool is now empty. There's no more transactions. The block is filled. The next step is these pesky roots that we talked about. So now the block author the block and can calculate and knows that this block is now final. I've done everything I want to do, and it can calculate two very important roots. It can get all of these transactions, Merkleize them, and get the root from that. That's our extrinsic root. And finally, it has a local state that is state n+1. This is the new state. It will Merkleize that, and it will also get the root from that. And that would be the state root which you will put into the block header. Is this clear? Good. All right. So then, okay.
Let's go with that one. So just make sure I understood.
Yeah.
So the runtime is then executed 2 times. One when he gets the transactions from the pool, and then later when the block is proposed, so the same transactions got executed twice.
Exactly. And the first time, but the key is that in the first time, it doesn't necessarily get executed. Like, it's up to the runtime to decide what it wants to do on the pool validation. But as I mentioned, the pool validation is like Wild West. It's like, it's like transactions is coming in. Like, any user can DOS, this like poor transaction pool. So what the runtime typically does in pool validation is just like do the bare minimum. Like, look, okay, is there a signature? Is the signature valid? And you have this again exactly in your assignment. What you have to implement in your assignment clearly asks you to do these things. The runtime would do like the bare minimum. Let's do a signature check. Can it pay for itself? And if it can, then it's good. I don't care later. And no state changes are relevant here, like, because we're just validating if it's like good or not. When we actually apply it, well, of course, then we need to execute it completely and just see what it is. See what it does. But yeah, typically, or another detail, the pool validation can be periodic. A transaction can be validated like 100 times, right? Because validity is something that might change, for example. Maybe the pool is programmed that I validate transactions, and if it's valid, good, but every 1 minute I revalidate it. Because you learned about nonce yesterday, right? Like in Ankan's example, a transaction might be valid now and invalid in 30 seconds. So,
so basically the node is constantly being broadcasted blocks and transactions in separate sockets, let's say.
Yeah.
And then at what point is it like, okay, now it's time for a new block? Because it collects transactions, and then let's say it's nominated. Let's say it's the only validator or whatever. Like,
yeah.
At what point is it like, okay, now it's time, it's enough transactions, or like what? Or
it's, it's like a good question, let's say, but I would say the concrete answer is like it depends on the consensus mechanism and one of the roles of a consensus algorithm is to specify who gets to author a block and when. So it's up to that part of the system.
So that would be another kind of like socket, or
I wouldn't call it a socket. I would say it's a rule that people adhere to.
Okay.
But the second answer I want to get, and it's a little bit more abstract, philosophical, but I think it adds to it, is that whenever, like, you know, I can run a Bitcoin miner in my computer now. I can tweak the software to author, like, just produce a block and put it out there every second. It's probably an invalid block because I can't get this non-stingy correct, but there's nothing preventing me from doing that. I think that's actually a good question because it illuminates the nature of these softwares being free and open to all. Yeah, I can do whatever I want, but the rest of the system is not going to accept it because it doesn't adhere to this consensus rule that we just talked about. So the short answer is yes, there's a consensus rule, you stick to that. The broad answer is like you can do whatever you want, but no one's going to take you serious if you don't.
So from a software design developer point of view, basically there's a function that is in creating a block and it's called at some point. Like by some mechanism, consensus, whatever.
Yeah, exactly. Yeah.
Okay.
And when and how often it's called, it's irrelevant to this lecture, I would say.
Cool.
Next to you.
So I have more general question. Like, after building a block, do we communicate with database again? Because you mentioned that Wasm runtime again executes and calculates the state, right?
So do we do
like
what again?
After the block was built, it's where it goes. It's supposed to go to import queue of other nodes.
Right? Then it's propagated back to the. Maybe that's a good addition to this figure. I like your suggestion. Once the block is built, it goes back to the networking layer and then it's sent to the rest of the world.
So communication with database node, it's goes only once in order to get the code for Wasm runtime, right?
Depends on whether you trust your block or not. Like if you fully trust your own block, you probably want to update it in your local database as well. But I think actually in implementation, usually authoring and import is very completely separate. As in you author a block, you push it to your network socket, as he kind of put, and at some later point, it comes back to you as like when gossiped as a, in a block, and you re-import it yourself. But you can also just re-import it right now if you want.
Okay, thank you.
But a good addition that you had to my diagram is that once everything is done here, there is a step 7, which is back here at the networking. So we have a new block. We want to now share it with the rest of the world.
Yeah, Kian.
Go on.
I want to confirm my understanding. So when a transaction comes to a node, that transaction is communicated to all other nodes over P2P, or first a node verify that it is valid, then broadcast to other nodes.
So the answer to that is interestingly exactly, well, it's a different answer, but the answer has a very similar tone and way of thinking to my answer. So the short answer is what nodes typically do is that they do this cheap validation, and if it's good, they keep it in their queue and also propagate it to everyone else. The long, more free-thinking answer is they're free to do whatever they want. Again, this is like, but then there are protocols also at the networking layer that if you keep sending me bad transactions, I'm just going to ban you. So it's...
Gotcha. And second thing, the transaction pool validation happens on the state of n, because n+1 will be being built in parallel. So
yes.
So that happens on n.
Yeah, and it happens completely at a different time as well. So I think these two it's important to mention that this step, like filling this list, kind of happens, I wouldn't say necessarily earlier, I would say it's a different process. It's happened asynchronously. Whenever Block Builder is doing its thing, this list is already there and it's already validated. Or it's easier to think about it this way. But yes, so long as block n+1 has not been canonicalized, it's on top of block n where everything else happens.
Okay. And also the transaction pool, does it consider sequencing like A transferring balance to B, and there's another transaction B transferring balance to C?
Yeah.
If A to B goes first, then B to C will be successful. And if second goes first, then first one will not be successful.
Yeah, we'll learn about that in the next lecture. We'll learn about that in the next lecture.
Okay. Yeah.
But the short answer is transaction pool at the node level, no, doesn't care about this because it doesn't even know transactions. The runtime can be programmed to care about these things.
So B2C will fail basically validation.
It's up to the runtime.
Okay. Thank you.
Yeah. Next lecture.
Does the node prioritize importing over authoring? I mean, if the queue is full, is it?
Yeah, I get what you mean, but I kind of don't know. I don't know. Like it's I think it does them in parallel whenever necessary. Like first of all, most nodes are not authors. That's in most proof of stake systems at least, or many proof of stake systems. Most nodes are just importing. They're not authoring. Like there's a smaller committee. I don't know, a few hundred, 1,000, 2,000. This is the scale of number of nodes that are authoring, and they're doing both in parallel. I don't think they, I mean, there's probably some implementation detail somewhere that I don't know about, but I don't know of any specification that says like this must happen. Like it's software, it's designing concurrent system, kind of. Okay, one more, and then we.
Hi.
You haven't.
So you said that the runtime is receiving transactions like one at a time as it builds the block.
Yeah.
And I guess, so that means that basically at some point when the block size limit is sort of reached, like some transaction like reaches that limit, it just stops at that point?
Yeah.
Okay.
All right, one more, then we should continue.
Where do you write the transaction pool validation code? Is it in the Wasm runtime?
In the runtime, yes.
Okay.
Yeah. All right, let's have a quick look at the pseudocode of what we just talked about. I mean, this one is a bit longer, but with all the explanation that we had so far, hopefully it should be pretty clear. It doesn't really fit, but there's just a small piece of it that's not in there. All right, so let's walk over it step by step. We want to build a new block, so we ask sort of our consensus component, hey, what's the best block that we already have? And give me also like the hash, the number associated with that. Then we get the state associated with the best block that we currently have. This is all repetitive. Then we get the code from that particular state. We stick it in a Wasm executor, and this is now our runtime. Then we start with the empty block. I'm kind of representing that with this like default in Rust. I mean, there's probably some header fields and so on in this, but I don't want to get into the details. So default, an empty block. And this is also declared as mutable, importantly, because we do want to mutate it as we author a block. And then this is the meat of this segment, or the important part of it. While some transaction pool iterator, however it is implemented, while you have new transactions, just give it to me. And this time I'm calling into a different runtime API with a similar syntax. It's called apply extrinsic. So we do it one by one. And we're assuming that this apply extrinsic is returning a result. And if that result is okay, we are pushing that transaction into the list of the transactions in the block. So block.extrinsic.push, this one that I just applied. And we repeatedly do this. I mean, there was some questions that, how long we do this and stuff. This is naively assuming we're doing it infinitely. Of course, in reality, it's not like this. The block size is limited. The runtime at one point might say, enough, you have to stop now, whatever. There's many constraints here. And finally, we get the root from the new root of this state that has now been updated, the right-hand side of that equation, and we stick that into the header. We do the same again for extrinsics as well, but for simplicity, I haven't mentioned it here. Yes.
This is a node view, right?
Yes, it's still all node view.
So how come the node pushes the extrinsics and pushes the next extrinsic and updates the block header and not the runtime?
Actually, that's a detail that is the inaccurate thing in this one, and my next slide corrects it. Although, in my opinion, I think it could happen. So updating the roots could happen either on the client or on the runtime side, on the header. The way that it's implemented in Substrate, it happens on the runtime side. But I don't see a fundamental issue with this last. Why it's not scrolling here? If you're referring to the last line, I don't see a fundamental issue with it either. Like, you know, the node is also capable of updating that root, as far as I can think of it, at least.
Okay.
Yes.
Yeah. I mean, I know it's pseudocode, but it should be like next transaction, right? When applying the extrinsic, because it's the same thing you get from the transaction.
I think I renamed it to extrinsic sometime, but yeah.
It's the same thing. They're not.
Yeah. This is just a typo.
Okay.
So maybe a silly question. Since when we say best block, right? So consists of best block, right? So are those best block has some attributes? That's why we're calling it a best block, or it can be say normal block. So it differentiate from a best block.
It's a normal block.
Just the normal, we are calling it as best block.
Yeah.
There are no such attributes which are attached to that.
No. Okay, but this is also again a detail of the consensus mechanism, right? Like most systems, as far as I know, have this rule that if we have finality, for example, knowing what's the best block is a bit easier, but typically at the tip you could have unfinal blocks, and usually everyone takes the longest chain. But again, it's irrelevant. There is some code that tells me what is the best block.
Yeah,
whatever is the rule.
Yeah, I just saw because it is like a best block mentioned, so probably I thought name has some.
No, it's just a normal. Just a normal. So this detail about root updates. Again, I'm a little bit doubtful if this is like more like specification or an implementation detail of Substrate. I'm inclined to think actually that this is an implementation detail, but one that you should know. So in the previous slide, we had some inaccuracies, specifically regarding how the roots are placed in the header. So the way that it works in Substrate is as such. So before we have this while loop and we go into like, executing transactions one by one, we call into another runtime API that's called initialize block, and we pass in a empty header, a raw header into it. And then there's another runtime API that we're supposed to call at the end of the block called finalize block, and this will return the final header for us. So this means that the task of updating the header and putting the right roots in it and whatever else is necessary is actually part of the runtime responsibility as well. Actually, now I got a spark of why it is the way it is, because the runtime, for some topics that we don't cover here, the runtime is free to actually put more information in the header as it wishes, and doing it this way enables that. So the runtime is free to not only put the state root and extrinsic root inside of this header, also put some other data in it. Yeah, actually the header is a iffy thing to upgrade. I think header is also not like forklessly upgradable. Or at least it needs to maintain some properties. Yeah. There's also another small mistake here. I think if I wanted to be really pedantic, I should have wrapped this, like both of these API calls, like initialize block and finalize block, in this state.execute. Because we kind of had this standard that all runtime API calls are meaningful on top of a particular state, and kind of violating it here, but it would have made the pseudocode much longer, or a few lines longer, so I didn't do it. All right, so I think this, let's go to the next slide. This will hopefully summarize the things that we've learned about block authoring. So it's composed of 3 runtime APIs. Initialize block, where we pass in a raw header. It's like, and this header doesn't have any roots in it. It only has a number and a few other fields that the node already knows about. Then we repeatedly call apply extrinsic, apply, until at some point the runtime signals back to us that enough is enough, you should stop now, at which point the node calls finalize block, and then the runtime will give you back the final header. And this final header has the right roots in it. And this is exactly, again, what you need to do in your assignment. So implement a correct finalized block with the right headers in it. All right, a small recap of some of these upgradability things that we've learned. So we've learned that the code can change, so the runtime can change. With it, the state definition can change. The location, which state key represents my balance, it can also change. That's okay, that's great. Or it's great from some perspective, it's great from the perspective of upgradability. Also, the extrinsic format can change. So the bytes that represent what is a transfer from my account to his account can now change from one block to the other, right? All the extrinsic format can also change. And this poses a problem which you already dealt with yesterday in Ankan's workshop, that this is terrible for all the wallets and all the applications that want to live out there, because they have to constantly deal with these upgrades. And what was the answer yesterday? As in, what piece of information was provided by all nodes to help with this? Okay. Yes, thank you. Metadata. So this was just my intro to introduce to you officially the metadata. So the metadata yesterday was more like an RPC that you called. You called into an RPC and the node gave you the metadata. But actually under the hood, the metadata is a runtime API. So the runtime always exposes this one API called metadata. And actually, interestingly, the return type is not specified, is opaque. It's just some bytes. And how it's interpreted is, again, is a contract between the node and the runtime. But the purpose of this runtime API is that the runtime should put some information in this VEC-U8, maybe as JSON, maybe as whatever, to describe itself, to give all the types that are necessary for an application to work with it. Right? So for example, the question of like, how can I get someone's balance from a particular runtime should be answerable using the metadata. You'll learn more about metadata next week as well. A small note, by the way, so this Polkadot.js apps, this beautiful dashboard that you saw yesterday, unfortunately, it only works with substrate-based chains that have metadata, have proper metadata implemented for them. Not only any metadata, the frame flavor of metadata. Therefore, if you run your assignment template and try and connect that UI to it, it will not work. And that's expected, because if you go and read your assignment code, you will see that this metadata runtime API is not implemented. You can actually try and implement it and return, I don't know, some random vector from it, and it will still not work because it expects a actual metadata, which, again, it's outside the scope of this assignment. So again, then this also adds another interesting nuance to the discussion here, that I mentioned that any runtime is only meaningful at a certain block, therefore any runtime API is meaningful at a certain block. Therefore, also metadata is specific to different runtimes at the block. So if, for example, a blockchain's runtime is rapidly changing, so every week there's a runtime upgrade and it's vastly changing the metadata, if you query the metadata now, a week ago, 2 weeks ago, you get different values. These are different metadata that describe the runtime at that point in time. So in principle, an application can work throughout the history. Yes, 2 different runtimes at 2 different blocks return 2 different methods. So I want to use this actually to go into another sort of interesting observation of this ecosystem, Substrate. This is, again, somewhat personal opinion. Substrate chose a radical path of upgradability, like optimizing to be upgradable. And it's great. It was a big part of my yesterday's lecture to like sell this to you as like, it's good for this and that reason. But I also mentioned some of the downsides of it. And this here, I want to emphasize one of the other difficulties that it poses. Building UIs, apps, exchange software, whatever, on top of these upgradable blockchains is a new beast for everyone. And Substrate and chains built with Substrate really push the barrier, push the limits there, let's say, because it's much more difficult. You get upgradability, but at the same time, all the softwares that or built around your blockchain need to also deal with that upgradability. If you look at the code for, let's say, this Polkadot.js API, this JavaScript library that can talk to substrate-based chains, it's orders of magnitude more complicated than, let's say, I don't know, Web3.js or something that works with a static blockchain, because it has all these code that like reads the metadata, it generates a bunch of like, I don't know, on-the-fly TypeScript types and whatever. Like it does like a lot of like dark wizardry to be able to just deal with this dynamicness. Right? I also know like some interesting stories when like people first wanted to integrate Polkadot, or maybe its sister blockchain that came earlier, Kusama, into exchanges. Like exchanges like had no idea like when like someone from like Parity's support team was talking to them first time that, hey, when you want to integrate Kusama, it might change. And they were like, what? Like it can change? As in like, because everyone was used to this notion of like, you know, blockchain is launched once and everything is static in it forever. Like, or that was the default. So I think it's an interesting observation that when you choose the path of radical upgradability, it also comes at the cost of all these opaque types, all this like, you know, you need this metadata and so on. So it's a trade-off, but it's an interesting one. And this is also where I want to wrap up this, like, why the node is blind. Like, why I call it the oblivious node. Like, why the substrate node is oftentimes blind, because it has to be blind to the things that can be upgraded on the fly. I already said this multiple times in class, so hopefully it's clear by now. And a like, kind of a systematic way to think of it is that we want our state transition function to be upgradable. Therefore, anything that is part of the state transition function is opaque to the runtime. So that includes the body of the block or anything that is part of the state. And the function itself, basically. And there are things that cannot as easily change. I will talk about these more further in this lecture. For now, just like only mention them a little bit. Like host functions, let's say. You know, this is not really part of my state transition function. Actually, changing host function is rather complicated. It will come in the second part of this lecture. For now, just know that what I just said about like upgradability, of course, doesn't apply to everything. It's not like you can upgrade anything you want and it's always like, you know, good and forkless. Header, I mentioned that it's a bit iffy, or something very low level, like changing your hashing primitive. I mentioned in yesterday's lecture that Substrate gives you all the tools to easily upgrade them, but there is a difference between like easily and forklessly, or easily and you have to like, you know, have a fork or regenesis your blockchain and so on. So all these things can be upgraded. Substrate is also very apt, very capable of allowing you to upgrade them, but they're not always forkless. Okay, this is the... Okay, so we've had 90 minutes. We have an activity, but I'm sensing maybe like a, I don't know, short break, and then we... Yes, okay, let's come back. Okay, while we wait for everyone to come back, questions, we can start with that.
So actually, I have a couple of questions, but one of them is regarding upgradability. So every author of the block can put his own code, right? Update the code.
Yes.
And then, like, how all other participants of the network could like validate it? So like, who is actually assessing that this code is okay, like is valid, is not malicious?
Everyone else. Because if the code is not the canonical code, it will produce a different output, right? So let's say there's a code that says, for example, whenever I receive a transfer, it will add 10 to it. It will double spend in my benefit. But then, again, like a lot of these questions go back to like, yes, a block author is free to be malicious, but everyone else is going to reject that block, right? Because when everyone else imports the block, they come up with this different state root.
Okay.
Although bear in mind, we check. Yeah, no, never mind. Too much.
And actually, another one question is regarding the slide 10.6, I guess. So in the code, yes, here, when we send to runtime, initialize the block with empty header, and then we finalize it there.
Yep.
So we kind of delegate part of the work to the runtime, right?
Yes.
And here we just update the block extrinsics, and runtime doesn't know that we pushed the transactions, right? We
The
just send the
runtime,
header.
this gray part, the runtime is receiving this extrinsics.
Okay.
Right? This gray part also happens in between. I mean, if you call initialize and finalize right after, it's like an empty block. You can do that, but it's an empty block. But if you in between call apply, then some transactions get recorded, and then probably the runtime in finalize block will put some state root in the header that corresponds to those changes.
Okay, thank you.
All right.
I had a question about the transaction pool next extrinsic. So at that point in time when you're iterating, is it?
A bit louder, please. Thank you.
Oh, sorry. Can you hear me better?
Yeah.
At the point where you're iterating through the transactions and you're doing the apply extrinsic, is that encoded? Because like when you push it into the block, is it already encoded or is that something?
Everything that happens on the node side only operates with VEQ8s as transaction. Like there's literally, I wish I could at some point maybe remind me on Discord, I'll send you a link. There's literally a type alias in Substrate on the node side that says type extrinsic, it's actually called opaque extrinsic, type extrinsic equal VEQ8. That's all the node does. So whenever it's also talking to the runtime, whether if it's validate transaction during pool validation or apply extrinsic during block authoring, it just passes this VEQ8 and crosses fingers that the runtime will decode it properly and do whatever it's supposed to do with it.
I guess I was asking because I was trying to figure out at what point we were talking about MEV before, and I was trying to figure out at what point would that actually be a factor for like
metadata, you said?
MEV, like what is it? Maximum extraction of value or something like that. Like, so if the node can't understand what that transaction is, at what point can they even manipulate the pool or the transaction?
So if you want to have something like MEV, or I say MEV, that's what I'm more used to. If you want to have something like that in substrate-based chains, you would need to consult the runtime for it. Like in other blockchains, their node just already knows what's going on. I think here you just need to consult the runtime. For example, you could build like custom APIs. This is actually all unexplored territory, by the way. There hasn't been a lot of like MEV related research or applications on Substrate or Polkadot parachains. I think it's an interesting avenue to explore for engineers. But they would need to talk to the runtime to do anything useful. They can't do it alone.
Okay, thanks.
Yeah. All right, so there's no, or immediately there's no lecture, luckily. I think it's also a good change of scenery. We've had a lot of lecture, almost 90 minutes. So next is an activity that I want you to do for about 15 minutes. You all have Polkadot SDK cloned from yesterday. If not, still not too late, please do it and also build it so you have most of the build artifacts ready. And I want you to find a couple of things in it. And by find, I mean you just do like Control F and find it. So the way to define runtime APIs and implement them, and similarly to define host functions in Substrate, are all done using macros. So actually it's here. There's a macro called IMPL runtime APIs. You also have this in your assignment. This is a macro that then contains an implementation block that implements runtime API. So search for this macro call, the part that I'm highlighting, and see what you find. See where you find it. Then the other side of this equation is this other macro called declare runtime APIs. Declare some things as runtime APIs. So see what you can find by going through this. Just 1 second before you start, though, by the way, because I see some people already jumped down. Well, I think it's in your benefit to wait until I finish. And for the host functions, just look for this. This is like a macro, is an attribute macro this time, a custom one called runtime interface. See where you can find it, and with this macro, you're going to find all the host functions that are defined in Substrate. So explore this for 15 minutes, and then we expect out of this activity to find the concrete example of the things that we talked about. So look for that runtime API that is meant to execute block or author blocks or do transaction pool validation, or look for that host, see if we can find that host function that is going to update the state. All right? All right, good luck, and I'll be walking around helping. 15 minutes.
Hello? Okay. Okay. So I'm gonna do what I asked you to do right now quickly to just show you around as well. But before we go further, how many people found the execute block API? It's good, a few at least. But we'll find that now together, so you'll see it exactly. Ideally, you have found two things. You have found like one declare runtime APIs where we declare, okay, there's a runtime API called execute block, and then you see a lot of instances where it's being implemented by different runtimes. Similarly, like host functions for storage. Does anyone like? Yeah. Host functions, yeah. It's annotated with this macro. Yes, did you find, for example, storage get and storage set and so on? No? Okay, well, I'll show them now. I mean, ideally, we could have used a bit more time, but we got to keep it going, so you just follow along with me. Let me see, this is a bit of a new setup for me, so let me adjust. So, a bit bigger. So close everything. So first, let's look for Deco runtime APIs. So you see there's like, and let's search only in .rs files. And there's a lot of instances of this, but if we just like, okay, it's kind of hard to fit it, but a bit smaller. So there's a lot of like runtime APIs declared by different crates and so on. But if we continue at some point, I'm just like jumping through them real quick. I honestly don't know when I'm going to find what I'm looking for, but I'm just keeping my eyes open to see if I will find my prize. No. Let's just, I mean, I first want to find a declaration, so let's keep it to that. Go, 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 go. Nope, 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 nope. A lot of them are in the documentations. A lot of them are, like, these are also used for tests. I mean, if I search by file, I can find it faster. But I'm trying to like emulate what you would have done. Okay, but I found one of the like juicy ones. So there's one here called Deco runtime APIs, and it's, as you know, macros are like custom syntax. So whatever comes inside of it may or may not be valid Rust. In this case, it's more or less valid Rust. So we're defining a trait. It's called block builder. And then inside of it, there's a method called apply extrinsic. This is one of the things that you learned about in class, and you will implement this as part of your assignment, or you will see an implementation of this. It also contains this thing called finalize block. You can already see the return type is block header, like a header comes out. You can also see the return type of apply extrinsic. This would also be an important part of your assignment. You would have to learn to work with this type. Interesting history lesson. You can see Substrate was British English up until some point, but it's got renamed to US English. So, you know, sometimes you see these old things. All right, let's continue. I want to find the other one that contains the execute block stuff. And this is also a good one. So this is called, again, Deco runtime APIs. Tagged transaction queue is the name of the trait, whatever. And then inside of it, there is a function called validate transaction. Again, you give a transaction as input and you get some return type. This is the one that the transaction pool uses. It seems like I went over all of them. I didn't find the one that I was looking for. Let me see if I can. I know that the trait is called core. Maybe I can. Okay, I guess I missed it somewhere. I don't know. But this is also the main one. So this is like the mandatory runtime API that all runtimes also need to implement. Again, it's like Deco runtime API somewhere, a trait. This time it's called core, and then inside of it we have this holy grail that we've been talking about all day, execute block. Interestingly, we see initialize block is also part of this one because it's used in other places other than block import. But block import uses the same initialize block. So it's like the core initialize block, and then it uses its own apply extrinsic and so on. Interestingly, metadata is also here. So I already mentioned that metadata is also a runtime API. You see there's another API for it. And so on. So now let's look at the other side. So IMPL runtime APIs. So, and I mean, there's lots of instances of this as well, but if you like just scroll, like if you look at the files in which instances of this is being found, you will soon realize every runtime has this IMPO runtime APIs. In fact, I'm just going to go to the assignment that you received and show it to you there. I believe this is my assignment template, which I was playing around with yesterday. Jeez, I need to fix these extensions. In your assignment, if you come to the bottom of the file, you actually have one of the same macro calls. Implement runtime APIs, and now we should be able to connect the dots. This is the core API that we were just looking at, which has the execute block. And then inside of this execute block, where I'm just forwarding the call for you to this other function called do execute block when you're expected to implement do execute block. Although in this case, execute block is actually complete. You need to just complete it for block builder and whatnot. You could also just add your implementation here, just add your code here. One reason that I personally don't do it is that Rust Analyzer or other IDEs don't work really well inside macros. So, the code in here is not really it's not really being interpreted. But if I go to this do initialize block, because it's normal Rust code, Rust Analyzer and stuff work a little bit better. That's just a personal preference, not a big deal. Similarly, we see inside of this IMPO runtime APIs, we also have the block builder being implemented and this tag transaction queue being implemented. The metadata is also being implemented, but as you see, I'm just returning a empty. I'm using default as the return value, which is basically an empty vector. So your runtime has no metadata. This is also why that Polkadot.js apps doesn't work with it. And there's a bunch of other APIs that are irrelevant for your assignment, but you can go and find the corresponding declaration and so on. All right, so that was about runtime APIs. Any questions or comments or anything? All good? So let's now look at the host functions. And okay. I mean, there's a couple being declared here and there, but I want to actually jump to a cluster of them that are in this substrate primitives IO crate. Actually, the first one that we find here is actually, again, this is an attribute macro, so the syntax is custom. But in this case, again, it's just a normal Rust trait. Actually, in this case, it cannot be custom. It must be valid Rust. But there's a trait called storage. And it has a bunch of functions, and these functions are exactly the things that we were talking about, like get and a particular key, and it returns some bytes as your return type. We see the key is just a slice of U8, just like a vector of U8. And if we go to this bytes, it's actually no, it's not. Okay, no, it's a little bit more complicated type. But end of the day, it's returning to us just the vec U8 as well. I mean, it's just a more fancy representation of that. Similarly, we had get, we have set, and we have clear. And I think these are all three that you need in your assignment. Now, the syntax to calling these is a little bit more custom. I'll show it to you, actually. It's a good time to then go back to the slides. I'll show it to you as a part of my slides. So with runtime APIs, hopefully it was clear. They have Deco runtime APIs and then the corresponding IMPO runtime APIs. In Deco, you declare a trait, and then in IMPO runtime APIs, you can implement it in different runtimes and provide some implementation. This I don't care about. Host functions are defined with this attribute macro called runtime interface, and when you want to call them, it typically looks like this. And this is just implementation detail of this macro of how it works, but you define a trait, and this trait is usually capital, or it is capital case. But under the hood, using this macro is actually converted to a module, so it becomes lowercase. So when I want to call this storage get, in reality it looks like this. SPIO storage with a small s, and then the function name. So you see this code a lot again in your, let me see, in your starter code for your assignment. I think you should have it somewhere. You can already see in your assignments, in the code that we have already provided to you, these functions are being used, like SPIO storage, I don't know, get some value, or, oh, this one is a bit more complicated. We don't care about it yet. Get some value, set some value, clear some value for me. And then there was also one to get the root. This is also an interesting one. You learn about it more tomorrow morning, but the ability to Merkleize your storage and give you the root is also something that's a host function. Like the runtime cannot do it itself, clearly because the runtime doesn't have the entire state. The runtime, but the node has the entire state. I mean, of course, it cannot interpret it, but the runtime issues a command to the node via this SPIO storage root, telling the node to, hey, Merkleize the entire state, give me back the root. And again, all of this is being used in your assignment already. You just kind of have to read it and then reuse it for your own purpose. All right, so with that, we can really like wrap up the real block import and block authoring runtime APIs. This is, again, more like a hint for you and in your assignment to know that block import calls into this runtime API, block authoring calls into these 3 runtime APIs in the order that is given here. Initialize block, apply a number of times, and then finalize. And yeah, the most important 3 host functions that at least you need this week, you need to learn them, are these 3. SPIO storage, get, set, and root. And clear. Actually, there's a 4th one. Okay, so with that, let's recap everything we learned so far. Just going to wrap up the first part of this lecture. The second part is shorter, and I'll do it after this recap, and then we'll probably go to lunch. So we learned further what is runtime API and what's host function, the definition, and so on. We use the examples of like updating the state, importing a block, and authoring a block to learn many things. You hopefully it's cemented also like these concepts just outside of Substrate. Generally in blockchains, what does it mean to import a block, author a block, how they usually work? But we also use them as we use them as an excuse to learn in further detail how runtime APIs and host functions are working in Substrate. So we use them as like a learning tool. And my favorite part, we cemented this idea of why the node is oblivious so often. Why does the node not know so many types and so on? So this was the last time this is one of those pieces where I hinted at it so many times in lectures, but today it was finally, you know, packaged as one fact given to you. We also learned a little bit more about the metadata. All right, I'm going to switch this to my previous setup, and then we continue the lecture.
Excuse me, I have a question. I'm a bit lost about what is the host function exactly. Here, what is the host function? What are the host functions?
They are the set of functions that the runtime calls to talk to the node, such as updating the state.
But these are these, can we change those? Can we add to them and
Oh, this is part of part 2, actually. Well, what do you think?
I mean, they should, I think, like, so there is the node and the runtime. The runtime is upgradable, but then we need to maybe update the node and add some stuff to our things, okay, right? How we run
let's jump ahead. No, actually, let's jump ahead. So I want to answer your question now, even though it comes further in the slide. So the scenario is I have a host function, and let's say I add a new host function. So the current runtime doesn't need this host function, but the next runtime that's going to be upgraded will need the host function. What does that mean? And usually the nodes don't upgrade. The nodes are oblivious, right? Can the nodes still be oblivious?
But usually they're not being upgraded, but we might upgrade them, right? Like,
yeah, we might, but it's not mandatory. But if we add a new host function, then nodes need to upgrade first.
Exactly.
So that's one scenario. Then another scenario is, what if there is a host function and we just change the signature? I don't know. Let's say there was this host function root. Let's say there is a new parameter to it. I don't know. Use binary Merkle tree or base 16 Merkle tree. Whatever. what happens then? So the old runtime wants the old host function. The new runtimes wants the new host function.
Yeah.
What does the node have to do?
Maybe we don't have override, but like override in Rust, we don't override functions. But is it backward? It's not backward compatible?
We want to remain backwards compatible because we want to be able to execute old blocks as well, right? One of the points of the blockchains is to be able to re-execute everything from Genesis.
Then maybe instead, we need to design this first, right? Like have a function in like the parameter in a way that.
I think you're getting into implementation, Dito. Just tell me what is the desired, like let's implementation.
The desired is to be able to upgrade it and be backward compatible with
support both.
Yeah.
So if we, for example, alter a host function, we need to support the old version and the new version.
Yes.
And when can we get rid of the old version? Never.
Yeah.
So that means host functions are like a huge commitment, as in because the moment a runtime uses a host function, in order to be able to re-execute that runtime and a particular block, you need to support that host function. So I think that's more or less everything I wanted to teach about host function versioning, but we kind of we went over it now. All right, so we're going to talk about a couple of like let's say consideration or more like consequences about runtime APIs and host functions and this separation. First one is generally speed. I hinted at this yesterday as well. The fact that using Wasm is in itself a potential overhead in terms of speed. But what I want to add to it today is that you also have to think of it kind of similar to like CPU registers versus memory, or memory versus disk. So there's like a barrier. You have to cross it. It's kind of slow. It's like, so within your WebAssembly, you have some local variables. If there's a stack, there's like some whatever. The moment you go over the boundary of calling into the host, it's like this slower, sluggish operation that takes more time. So you need to be like conscious of how often you go over this barrier, and that will influence the speed of your program. Actually, yeah, this is more about this diagram. So you can think of really the host and the WebAssembly as like two different components that whenever they talk to each other, it's a slightly slower operation. I mean, how slow it is, I don't want to give you like a particular number of it takes this many milliseconds. I actually don't know the number, but it is noticeable. It's non-negligible. Also mentioned yesterday that WebAssembly execution itself there are different generations. Like interpretation is generally safer but slower, but you can also compile WebAssembly, then it's almost as fast as native. For now, you should just know that these options exist. Later, when you learn about Polkadot, you will learn, for example, which one Polkadot uses, and so on. So, but you already learned about contracts. So contracts, was it told that they use interpreted WebAssembly? Right? Like, as in, no? Okay, well, I can, yeah. I mean, it's not like let's say, a game changer, not a piece of information to know, but so interpreted WebAssembly is like executed command by command. It's safer because if the code is malicious, you can bail out at any point you want, but it's slower. The same way that compiled languages are typically faster than interpreted languages. So when you're dealing with foreign code that you cannot trust, you typically want to interpret it. Whereas if you trust that code or have better guarantees of that code being not an infinite loop, for example, then you can compile it. All right, so then there's this interesting trade-off as well. So some of the host functions are for operations that are time-consuming, potentially, such as hashing or cryptography operations. So if you look at all the host functions in the same SPIO whatever, you will find like also SPIO hashing, SPIO crypto, and so on. And these are just like normal, if you want to hash some data, the runtime can pass that data to the host, to the node, and ask the node to hash it for it or verify a signature. And the question is why? Couldn't the runtime do this itself in this case? Because it's just computation, it's just some code. The answer is that yes, the runtime could have, but it's like a trade-off situation. Is it faster for the runtime to do it itself? And when the runtime does it itself, it's executing within WebAssembly, so it's a bit slower. Again, also depending on whether it's interpreted or compiled. If the runtime passes it to the host, there is this cost of copying it over, But then the host is super fast because the host is like native and it's running on hardware directly, so it's a bit faster. And then back. So sometimes it's better to copy over, do it outside, and then copy back. Sometimes it's better to do it local. Actually, as far as I know, the decision to do hashing and crypto signature checking and so on the host side is at this point it's pretty wrong. Like as in it doesn't make sense anymore. It's a bit historic. So because when Substrate and Polkadot and so on started, this compiled WebAssembly stuff wasn't around. It was interpreted. WebAssembly was like 10x slower than native, and I think nowadays it doesn't make sense anymore. I think someone mentioned yesterday that some things are outdated. This is one example where we know it's outdated, but it's waiting for new engineers to go and fix it.
So do you usually run benchmarks to know what things to move out and stuff?
Yeah, some people have run benchmarks or.
What's the mechanism in which code is run on the because you were saying now some things we would run on the node, some things we would run on the runtime. Like from our point of view, like let's say for this assignment or when writing this kind of stuff, how do we actually run code on the runtime? Is it like when we pass like a function in like a callback or like some logic to be?
So if you're asking specifically for this assignment, you're only asked to code the runtime. So you are, unlike my pseudocodes, in the runtime. You're trapped there. Everything you write is inside the runtime. So you're not really dealing with this situation.
Okay. And in what situation? So to make that decision, that would be when one is writing both separately, or like.
So
or is there part of the some application, some program that like basically you would have an opportunity to do both, like delegate some call to the runtime or something like that?
So I think it's helpful to think about these things from the point of view of the runtime. So you are the runtime, you typically have two options. You either do something yourself, or you write a custom host function that does it for you, and you then call that host function. And as I mentioned, adding host functions is a big commitment, so you need to really think about whether you want to do this.
Yeah, and like, so just for example, like the impl runtime stuff that we saw now, these are how we generate host functions?
So those were about runtime APIs. Yeah. This is more about host functions.
Okay.
I think
I'm just trying to figure out where do we have. So for example, here, what is a host function? Like the storage, for example?
Storage is one of the host functions, yeah.
Cool.
All right. Yeah. All right. So come to me afterwards if there's. All right. Introducing something new that is going to be deprecated soon, but I think it's still worth understanding. So, whenever you build a substrate-based project, you have the runtime code in Rust, which you compile to WebAssembly, but you can also compile it to native code. We call that the native runtime. So every substrate node is packaged with a native runtime as well, and it's sitting there. And this native runtime, so all runtimes have a version. This is something I will allude to a bit later. I think yesterday was also either mentioned or maybe because of time we couldn't talk about it. But long story short, very intuitively, every runtime has a version. It says I'm version 2, I'm version 3, whatever. So native runtime has a version. The real runtime, the Wasm one that we get from state also has a version. And what the node can do is, whenever it wants to do a runtime API, it can look at the versions, and if they match, it can optimize it by just calling into the native runtime. So let's say the node wants to execute a block, and the native runtime that the node already has with the one that is, is in this Wasm thing, and it's sitting in the database, and it has to go and grab it and put it in the executor, they're the same, so it can just call into its native runtime. So this native runtime, again, it was put there, added there, when 2017, everyone thought Wasm is notoriously slow, and this was an amazing optimization at the time. If nodes were kept up to date, they would have executed 5 times, 10 times faster. It was amazing. But now, because Wasm is almost as fast as native, this is just code overhead. The Substrate client code is littered with, weird abstractions to support this, and it's actually being getting rid of nowadays. So I think very soon the native runtime will be gone, and this will also enable a bunch of other features that we are interested in. So know about it, but at this point, yeah, know that it's also going away. Yes? So when the native runtime wants to call a host function, it's the same thing, but then that host function is just a normal function call because it's all in the node. It's all like, purple boxes. It's all like, yeah, can you give him the mic?
So to call the native runtime, because the Wasm runtime itself has access to host functions and it has access to the native runtime.
So the Wasm runtime has access to the host functions. The native runtime also has access to the host functions. I mean, I don't have an explicit arrow here, but the native runtime can also call to the host functions.
Okay, so from this picture,
yeah.
how does the runtime call the native runtime?
The runtime doesn't call the native runtime. So the process starts here. The node wants to call execute block.
Yes.
Right? So it looks at the version of the Wasm runtime.
Okay.
It also looks at the version of its native runtime. If they are a match, it's like, okay, I'm just going to use the native one. In fact, that's already simplified. In the CLI flags, you can configure this. If the versions don't match, it's a non-starter. Mm-hmm. It's like gone. Native runtime is useless, throw it away. If the versions are match and in the CLI parameter you wanted to, it will use the native one. And when you're using the native runtime, both runtime APIs and host functions are the same thing. They exist, but they are no longer this complicated process where you have to, go over the Wasm boundary. It's just a normal function call.
Okay, just to understand this correctly, our Rust code, we package it into Wasm runtime, and we also compile it locally to have a native runtime the same.
Yes.
Okay, so it's okay. I was a bit confused. I thought it's some other.
I have a. Let me jump a little bit ahead. I have an interesting diagram somewhere. Where is it? This guy. I think this guy might explain it well. So this is like a version of the diagram we had like yesterday. You have the node software. It has a version, which is actually irrelevant to everything I said. This is like a Semver, whatever. The node has a native runtime, and this native runtime also has a version. And then finally, there's a Wasm runtime, which has a version. If these two have the matching version, we have the option to optimize. If not, then it's a non-starter. All right, so I mentioned that every runtime has a version. This is just a struct that is representing that version. Again, in your template, you can actually find this. The only parts of this struct that I want you to focus on is just that there's something called specification. So there's like a specification name and specification version. And this is the only two things that we care about. So two runtimes are equal if they have the same spec name and spec version. This is also why in this image that I just showed earlier, you can see the native runtime and the runtime, the version number is just one number. It's not like 9.4 point whatever, because the spec version is just one number. So what we mean by the version of the runtime, we actually mean the spec version of the runtime, or we refer to it as the spec version. All right, let's go back again. So with this code, which I'm going to give you a few seconds to read first. But this is like a pseudocode representing what I already told him as a response to his question, that if we want to use the native version, native runtime, there's always this if statement blocking it. So if the versions don't match, it's not a question. We have to use the Wasm runtime. If the versions are a match, and we want to, we can do it. Yes, the days of the native runtime are numbered. It's going away. Interesting question. This is, again, when we get rid of the native runtime, this becomes irrelevant, but at the moment it is relevant. So you won't, at least yet, you won't learn exactly to do a runtime upgrade. But when you do it, one of the things that you're expected to do is to increase that spec version. And the question is, what will happen if you forget to do it? Yes. Yeah. So let's say you have a runtime. you have a runtime. You change something in it, and it's a breaking change. So it's now a different runtime. It's a different specification. If you forget to bump that number spec version, something will go horribly wrong. And now, can you say it? Can you rephrase again? Or if you have an answer, can you say it?
It's the same, right? Like
okay.
Basically, if you changed like the signature in the runtime, and then the native is the old one, but when we check, you will try to call the native with something new, and then
so we basically confuse the native and Wasm if we forget to bump the spec version. So the node might become confused, thinking, oh, my native runtime is the same as the Wasm one, whereas the Wasm one has actually changed. So the rule of thumb I want to point out here is that you absolutely must bump that spec version whenever you're changing your runtime and upgrading it.
So if we don't change the version and when we compile it, then won't Wasm and the native both will have the same number again?
Sorry, can you say again?
So we don't change the spec version, and then we do compile after every change. So both will be generated with the same version again. Okay. So current version is 940.
Yes.
Okay, in the code, and I don't change it. Okay, and then I compile the node, which will produce Wasm runtime as well as the native runtime.
Yes. And they would both be again 940.
Yes, they will again be 940.
Sure. But if you have already made a change, and for example now you want to publish that Wasm runtime through governance and enact it on chain, that would be an issue. Because some nodes were already running something different that they thought is 940, and now you're publishing something new that is also 940. So they're gonna those that use the native runtime are gonna be screwed in this situation.
Oh yeah, got it.
Right? Yeah.
Thank you.
Okay, so kind of already covered this as well. So there's like 3 different versions that are in Someone want to speak? Okay, let me just finish this then. There's 3 different versions that are in this equation I need to know. The node version, and this is just like a software version, it doesn't play a big role in any case, but the node has a native runtime, at least these days, and that native runtime has a spec version, you do care about that, and there's the WebAssembly runtime as well, the canonical runtime, and that one has a version as well. And these 2 are spec version, which is just a number, the node's version is just like a normal semver thing. Also in this example, you can see I put different numbers for native runtime and the real runtime, which means in this case the native runtime is useless, because it's already out of date. So now if you...
my confusion on this runtime version. So suppose whenever we are making any changes to the runtime and there is a new version spec with it, and now when it's communicated with the node, so suppose the same version of spec is not there in the node. So how does node syncs with the runtime on the version side? Like, so you said 942, it has to show, it has to make sure that it should have, this version spec over there so that it can actually run the latest spec.
No, I mean, no one has to run the native runtime. It's completely optional. If your native runtime is out of date, tell me if I'm understanding your question right. If your native runtime is out of date, it's out of date. It's fine. You will survive by just running the WebAssembly one.
Okay, got it.
Okay. All right, this is just like for you to look at later. There's this website called the Polkadot Telemetry. You can go and it has a list of all the nodes in all the different networks running substrate-based chains, and it has a column that's like version. And this is like the node version that we have here. It's not even like the runtime version. Contrary, if you go to this beautiful Polkadot.js apps thing that you had yesterday and connect it to one of the production networks, for example, Kusama. I mean, this screenshot is a bit old, but it still conveys the message. You can see on the just like on the top left, you have like Kusama / a single number. This is like spec name, spec version. But on the other side, actually, you have like the node software's version, which is like Parity Polkadot version 936. So this is like the version of the node, which kind of we don't care about, or no, at least in the context of this lecture, we don't really care about it. Whereas on this side, the number and the name that we have here, this is the runtime details. Again, spec name, spec version. All right, this is also a recap. I wanted to pose it as a question, but in favor of time, I'm going to answer it myself. Again, like let's say there's a new node version coming out. So Parity is developing nodes for Polkadot, for example, and Parity makes a new release. What needs to happen? Nothing really, as in, except when there's infrequently a breaking change on the node side. People eventually upgrade. Everything works, business as usual. There's no rush for anyone to upgrade. It's all good. And what happens when, and then in this process, the runtime stays the same. You can upgrade your node from one version to the other. It would still treat the runtime similar way. And for example, your runtime code doesn't even understand that the node has changed. Nothing needs to. And then you also have the opposite separation as well. What happens when, as it is nowadays, the Polkadot Fellowship releases a new runtime for Polkadot? Do node operators need to do anything? No, they're running their own software. It's the new version eventually is submitted to the chain as a transaction, kind of similar to the set code. There's a voting process. If it goes through, the code will change, but the node software doesn't even understand. It doesn't even realize that this has happened. All right, one of the final considerations, but it's a very important one. Also, it becomes very important next week in Frame. I can already tell you this is one of the things in Frame that if in your assignment, for example, you make a mistake about it, it's going to significantly impact it. So pay attention. Is panicking. So Rust code, when it aborts, we call it a panic. The Wasm code generated by Rust can also panic. And question is, what will happen if we panic, and what are the consequences? Seems like I jumped a few slides. Yeah, it started from here. Sorry. And the question is, so you were looking at this from the nodes perspective. We're calling into a runtime API, and if that runtime API internally panics, what will happen? So in order to analyze this, I'm going to look at it from the perspective of, let's say, validator or blockchain economics. Like as a validator, what is your wish? Or as the node in this network, what is your wish? Looking at it from an economic perspective, nodes and validators are fine to perform operations, to execute some code, to spend their valuable resources like CPU time or whatever on user transactions or whatever work that needs to be done, as long as it's paid for. As long as that's basically what blockchains do, right? Like in some way, incentives, exactly. As long as there's incentives for it. This is at the deep level how all blockchains are working. We're collectively putting like little pennies in a bucket, which is then separated among, I don't know, some block authors or some entities to run the network for us. I mean, it could be very decentralized, it could be then very centralized. That's a different spectrum, but under the hood, that's all that's happening. So everything is fine. The mindset that I want you to take is that everything is fine as long as it's paid for. Or everything is permitted as long as it's paid for. All right, so this is just like written form of that. No validator wants to waste their time. And when you're authoring blocks, sometimes it's unavoidable because you're getting these foreign transactions. And for example, if the transaction is garbage, you need to do a little communication at least with the runtime to realize that it is garbage. So you need to waste like a fraction of a second maybe. But if you realize this transaction was bad, you want to immediately discard it and you like throw it away. Contrary, the expectation is that if the block authors realize a transaction was bad and wasteful, as in it wasn't economically feasible, they wouldn't even put it in a block. So the expectation is that at that level, like the block authors will not put bad transactions in the block. All right, I'm just going to continue myself. I think my slides, I can't follow my train of thoughts from there. So when a panic happens in a runtime API, what happens is that the Wasm instance is killed, and whatever state changes happened as a consequence of that are also reverted. So it's almost as if nothing had happened. So let's think about it. If, for example, you have any transactions in a block, that pay their fee, and as the block importer, you're like, yes, you paid for your fee, it's all good. But the last one panics, this whole block execution becomes discarded, and everything that you've done so far is a waste of time, was a waste of time. So this is why, for example, when you're importing a block, you're absolutely not going to tolerate bad transaction in a block. And it's also expected from the block authors to not propagate any block that has this property. It's a little bit more intricate when you are the block author, because as the block author, you might have this situation when you're putting transactions one by one into the block, and one of them might panic internally and just apply extrinsic, and then you waste a little bit of time, but you don't want to repeat. You don't want to repeatedly, waste your time like this. So, with this information in mind, if you have a user-reachable code in your runtime, like for example, a transaction where it does a bunch of compute, and in the last line it panics. What you can do is you can just send infinite numbers of this to your block authors, and they're gonna constantly try and build blocks using this. It's just gonna waste a few milliseconds, oh, panic, never mind. Everyone else will not suffer, but the block authors will significantly suffer from this. So one rule of thumb is that in any user-reachable code, there should be no panics, because then your block authors can become easily DOSed out, or they can be griefed. Let me repeat that or paraphrase that. I feel like that was a complicated thing, and I kind of get at it with some intro. So you have a transaction, a user-reachable code that panics eventually. I can, as a user, send many instances of that transaction to the chain, and that transaction might, for example, have fee payment associated with it, but that fee payment is also going to be reverted because that transaction panics at the end. So, whenever the block author is even trying to put this in a block, it's going to waste some time, panic, oh, no fee payment, no nothing. So in user-reachable code, no panic. This is the rule of thumb you need to take, and a little bit more, well, actually, more importantly, but a little bit less likely to happen, there's also this initialize block, finalize block runtime APIs that are mandatory. No block can be authored unless if these runtime APIs are successfully executed. If you have a panic in these code blocks, then then no one can produce any blocks. Then your blockchain is basically stopped. In initialize block, finalize block. I think it's only these two, but generally speaking, in mandatory runtime APIs that must be in your must happen. Like a transaction. Okay, so this is the conclusion slide. Let's pause here, where we have these things. Example other than transaction? I don't think so, because those are the main two sources of your state transition, are transactions and automatic things that your runtimes do. So the automatic things are the uninitialize and unfinalize, do some things at the beginning of the block before you do anything else. Do something at the end of the block when everything's done, and then during the block body. But my point is that, or one of the points I want to get through is that, if, for example, somehow your apply extrinsic panics, because your transaction pool is flooded with this panicking transaction that is terrible, the worst thing that you do is you author empty blocks. Initialize block, finalize block, done. You just move on at least. And then you can deal with the problem. But if you panic on initialize, it's done. It's and recovering from that is it's a situation you don't want to be in. So the first line of defense is actually us as runtime developers making sure we don't write a code that panics in user-reachable codes. But the node also has this protection, which is that validation, transaction pool validation, which is this initial. So before any node tries to author a block, it calls this other runtime API validate transaction while the transaction is in the transaction pool. And in that point, hopefully any bad transactions are filtered out. So this will be repeated next week multiple times in the frame lecture as well, but this is the conclusion that I want you to take away for now, and hopefully I have gotten through why exactly. Yeah, it's all covered. Yeah, I also covered this, but I think this diagram might help it a little bit better. I'm trying to portray like the trust situation, you know, between when you're the block author, between you and the transaction pool, it's Wild West, you know, like these are some transactions in the pool that I have the least amount of trust on. Like they could be garbage. As far as I know, they could all like, you know, trigger all sorts of bad things. But when you author a block, hopefully you're supposed to go through this Wild West of transactions and find the good ones and then put them in a block. And then when you're importing a block, your tolerance is much lower, as in you expect the block author to have already filtered out all the bad transactions for you. Yeah, you even see this in your assignment. I want to just hint at it, but without going into too much detail. If you look at your execute block in your assignment, it loops over the transactions, it would execute them. And you will see exactly that if any of those transactions are not successful, it would actually bail, it would panic. Which means the block, when you're importing a block, you are expecting no invalid transactions to even exist. Yeah. All right. Can we get a...
I'm just thinking about smart contracts where anybody else writes the code and how the flow will be same considerations, or I'm not able to...
And in a smart contract, the trust levels are very different because you don't even know the code. So here we're talking about trusting ourselves, right? Like I'm the runtime, I'm the blockchain, my runtime, I trust my runtime. It's only a matter of making a mistake and making a panic available in it. A smart contract is like foreign code that, as far as you know, can be like a malware. So it's a completely different analysis there. Now, if you tell me exactly what is, like, for example, your question, maybe we can try and answer it.
So some smart contracts can call the extrinsic as it is.
Which extrinsic? Like their own extrinsics or the runtime?
APIs.
Or runtime APIs?
Yeah. If I'm not wrong.
Okay, yeah.
So do we need to consider anything? I don't have a specific question. The question is like in keeping in mind a smart contract, do we also think something else? Or?
Okay, I don't have any thoughts around that at the moment.
Okay.
Okay.
Yeah, Mauricio. So my question is on the last slide. While block importing, we have somehow confident the node filtered some panicking transaction or bad transaction in the mempool, the pre-checks and everything, right?
Yes.
So this scenario which happened to me, okay, it was a parachain though, but then the same logic. The thing is, the transaction went and everything, but then while executing, while dispatching the extrinsic and the transaction, like it panicked and it like stopped producing any blocks and just stopped the whole chain, like halted, like didn't do anything extra. So that transaction was pre-validated in the transaction pool, went through, but while dispatching, it panicked and it stopped the chain. So can we while importing, are there any checks, like extra checks to kind of ensure that this thing
no extra checks, but I think you're talking about something that I jumped over here thinking that I covered it, but maybe it's good to repeat it. So, but I don't need the slide, let's just listen to me. There's actually I can best explain it here. There's 3 steps here, right? You have transactions that are in the transaction pool. At some point, someone authors a block with it, and at some point, someone imports that authored block. And I did say that, you know, our trust, our confidence at correctness of this single transaction in this spectrum increases, but at neither step you can trust the previous guy to have done their job honestly. So there's 2 outcomes to this. One is that the block author, whatever checks happened in the transaction pool, the block author repeats them. This is also part of your assignment, and the assignment description explained this. Hopefully some of you have already seen it, that you're asked to, for example, check the signature in the transaction pool phase, but you're absolutely asked to repeat it when you're authoring, because you don't know if this ever happened. You don't know when it happened. You don't know, this, whenever you're authoring a block, you're not trusting the previous step to have done it correctly. And then the other consequence is something that you're more familiar with. whenever you're importing a block, you absolutely re-execute all the checks and all the transactions because you don't trust the author to have done their job correctly.
But one thing, the code is automatic in the transaction pool. Like periodically, it rechecks the transaction in the pool, right? So if we redo the thing again, authoring, aren't we like just wasting resources and repeating
No,
ourselves?
because some of these checks are valid now, but they're not valid in the future.
Or like, for example, like
nonce.
checking validity and stuff, right? Invalid nonce. Okay.
Yeah, take a simple example, nonce, or even fee payment. So let's say transaction pool must check. This is an assumption. I mean, it's actually true, but hypothetically, transaction pool will check that all transactions, not only they don't panic, they can pay for their fee. But and the panic thing, okay, I mean, it's probably if they don't panic, they will not panic in the future as well. Although even that is a bit iffy, if you have malicious code that says, panic after a certain time or whatever. But even the fee payment, the transaction pool verifies now that my transaction can pay for its fee. In 5 minutes, that I may have already drained my account from another transaction, so my fee payment has become invalidated. So this is why the authoring phase must repeat the check that I can pay for my fee. And if I can't pay my fee while authoring, then that's my transaction is like, nope, sorry.
Okay.
All right. So this is the segment that we already covered to one of the questions, like altering host functions. Maybe I can just jump to the conclusion of it, which is that host functions need to be kept forever. So recap, if you add host functions, it means you need to update all your nodes first so that nodes are already ready and they have the new host functions. That's already a bit unfortunate, but it's not terrible. But if you, even more consequential is that if you alter a host function, for example, change the signature or like break it in a non-compatible way, you need to support the old version and the new version, and you can never get rid of the old version. Unless if your blockchain governance or community collaboratively decides that we're just going to checkpoint it. This is something that, guessing it hasn't been discussed, but it's an interesting thing. Like people especially in the older blockchains like Ethereum, this is a topic that, as far as I know, has been discussed a couple of times. As in, the state is massive. Like even the block history is like terabytes already. Why don't we just take a block in, I don't know, 2020 and say this was the genesis. Everything beforehand, we just kind of agree that we don't want to verify it again. I mean, it goes a little bit against some of the don't trust anyone ideologies, but just from an engineering and performance point of view, it's kind of sensible to do it at some point. So unless if you do such thing, you always need to keep the old host functions because you want to be able to re-execute all the old blocks as well. All right, so the last pieces of this lecture. All right, again, in favor of time, there's a little workshop, but I'll just walk over it, like as in I won't execute it live. I have the instructions here for you to go and grab a substrate-based runtime. In fact, Polkadot's runtime is the one that I use myself, and use a command that's called Wasm to wat. This is so wat is like WebAssembly text. It's like a semi-human readable version of WebAssembly. And if you run this thing, it would output like a long code, like wat code for you. And if you grep for it, like search in that file for import, you will find the list of functions that your WebAssembly module is importing. And what are these going to be? These are going to be all these host functions. So these are the functions that are imported into your WebAssembly blob. So you get a list that kind of looks like this. And some of these functions that are imported in your WebAssembly hopefully are familiar. I mean, the name here doesn't really matter, or it's not like there's some, how can I say it, like implementation data, like why are all the names prepended by ext? I don't know, it doesn't matter. I think it stands for external, whatever. But point being that there's some of them called like ext storage append, storage get, storage root, storage set. Right? And these are all the host functions that we declared somewhere in our substrate code, and at the WebAssembly layer, they are represented like this. And you could also do the opposite. So if you run the same command, but this time search for the word export in it. I can't do it. Like you can just see at the top here. Search for export. Now you're going to see a list of runtime APIs that any WebAssembly blob is generating. It's pretty interesting to see, especially when you add like your own custom runtime APIs and so on later in your career in Substrate. You can always like look at it here. But similarly, there's some naming convention here. Like if you remember, there was a trait called core, and then it had a function called execute block. So the way that the naming convention works is to use a trait name underscore function name. But yeah, this doesn't really matter, but hopefully you can connect the dots already, like core execute block, core initialize block, block builder apply extrinsic, block builder finalize, and there's a bunch of custom stuff, but yeah, transaction queue, validate transaction. So these are like all the same runtime APIs that we already saw at the low level of WebAssembly. Quite interesting to do. Especially when you build your first parachain in 2 weeks. It's quite interesting to go and then repeat this process, because a parachain has further runtime APIs, or some special one, and you will be able to see those as well. So this also I'm gonna explain what was expected here, but we won't do it now. It would be for you and in your free time to try. But as I mentioned, so panicking in user reachable code is like kind of forbidden. But there are places in the runtime where we panic. We expect a panic, and we do it intentionally. And that's because if that code is reached, it means, for example, the block author has done something malicious. So we actually want to bail, and then that would be like a punishment for the block author, because that block would never get imported. So there's a few places in runtimes where we actually do panic, and it's expected. And this activity is asking you to go and try and find them. It's insightful, but we won't do it right now. All right, let's do a recap and then wrap it up and go for lunch. So we learned some considerations, some further details of the WebAssembly meta protocol, namely the speed, the fact that WebAssembly itself could be slow given depending on how it's executed. And the new thing that you learned was that going over the barrier of Wasm is like an extra jump, so you need to be aware of that. Native runtime and versioning, although versioning is important, you should know it, but native runtime itself is going away. Panics, which are super, super, super important. I gave you this intro with like economics and how everyone should not waste time. That's also important to know. But if you just want to know like the TLDR, it's like don't allow user reachable code to panic, because then your validators would inevitably waste their time executing that code. And then anyone can freely trigger that, because there's going to be no fee payment associated with that. And we talked about host functions and how altering them is like a big commitment, as in you will never be able to get rid of the old version. And we had some activities.